Morning, students. So far, we discussed about the three units. Okay. So earlier unit is linear time invariant systems. Okay. So we already completed linear time invariant systems in the last class. Okay. Now we are going to discuss about the fourth unit, that is correlation and sampling theorem. Okay, correlation and sampling theorem. So the topics involved in this unit are what is autocorrelation, what is cross correlation of functions, then properties of correlation function, energy density spectrum, Parseval's theorem, power density spectrum, relation between convolution and correlation, detection of periodic signals in the presence of noise by correlation, extraction of signal from noise by filtering. Then coming to the sampling theorem, in sampling theorem we'll discuss about the graphical and analytical proof for band limited signals, impulse sampling, natural and flat top sampling. Okay, reconstruction of signal from its samples, effect of undersampling, that is aliasing, introduction to band pass sampling, and problems related to the above topics. Okay, these are the topics involved in this fourth unit, that is correlation and sampling theorem. Okay, correlation and sampling theorem, right? Okay, so these are the topics involved in this unit. Okay, so next coming to the correlation. What is meant by correlation? Correlation. Correlation, or it is also called as a signal comparison. So we'll compare two signals by means of some properties. Okay, so that is called correlation. The signals may be compared on the basis of similarity of waveforms. Okay, so suppose we take two signals. So if the waveform is same, then we can compare these two signals are sinusoidal signals, two signals are stereo signals, like that. So on the basis of uh, similarity of waveforms. This comparison may be based upon the amount of the component of one waveform contained in the other waveform. See, let us take two waveforms, x1 of t and x2 of t are two arbitrary waveforms. The waveform x1 of t contains an amount of x2 of t of waveform x2 of t in the interval t1 to t2, where c1 to equal to integral t1 to t2 x1 of t into x2 of t dt by integral t1 to t2 x2 square t dt. So this concept was already discussed in our first unit. With the two signals or two vectors are orthogonal to each other, then the condition is C1 to equal to, here these two are waveforms, so these two are signals x1 of t and x2 of t. There also we'll discuss about the analogy of two signals, analogy of two vectors, like that. That is also called as similarity. Similarity of two signals or similarity of two vectors. So taking the same concept here. So if the two signals are compared, if you want to check the similarity between two signals, then the condition is the C1 to equal to the ratio of integral T1 to T x1 of T x2 of Tt by integral T1 to T2 x2 square T dt. Let it be considered as equation number 1. If the numerator is 0, that is integral T1 to T2 x1 of T into x2 of T dt is equal to 0, that is C1 equal to 0, then the signals are called orthogonal signals for the specified interval T1 to T2. So orthogonal signals means here the condition is C1 equal to 0. These two are perpendicular to each other. These two signals are perpendicular to each other, right? These two signals are perpendicular to each other. Then we can say that these two signals x1 of t and x2 of t are orthogonal to each other. Orthogonal signals. These two are called orthogonal signals. Okay, right? So next, the comparison is completely depends on the numerator of equation number 1. Numerator of equation number 1. If integral t1 to t2 x1 of t x2 of t dt is equal to 0, that is c1 equal to 0, then we can say that these two signals are orthogonal signals, or these two are mutually perpendicular to each other. These two signals are mutually perpendicular to each other, right? In general, we are interested in comparing the two signals over the entire interval. Entire interval means that is from beyond the specified limits, that is from minus infinity to infinity. So the numerator becomes integral minus infinity to infinity x1 of the x2 of the dt, okay, for the entire interval. That is considered as equation number 2. So let us take x1 of t is like this. This is x1 of t, it is a sinusoidal signal, and x2 of t is like this. This is also sinusoidal signal with time delay t. So two signals x1 of t, x2 of t are given. So these two signals are same signals, same in waveform, that is sinusoidal signals, but the second waveform is delayed by t seconds. Okay, capital T seconds. The above two signals are identical except that x2 is delayed by t seconds with respect to x1 of t. If we compare these two signals over the entire interval minus infinity to infinity, it is zero. That is integral minus infinity to infinity x1 of t into x2 of t dt, which is equal to 0, right? So hence, in order to search the similarity between the two signals, we must shift one waveform with respect to the other waveform by various amounts. So test signals, test integral is modified as test integral. This is called test integral. J12 of tau. This is test integral. J12 of tau is equal to integral minus infinity to infinity x1 of t, x2 of t minus tau d tau. Let it be considered as equation number 3. This is a test integral. So the test integral will be modified like this, where tau is a searching parameter. Tau is called searching parameter. This equation number 3 is called cross correlation. Okay, cross correlation. We are comparing the one signal x1 of t with another signal x2 of t. Suppose x1 of t is compared with the x1 of t itself only, then that is called autocorrelation. Okay, so but here in equation number 3, so that x1 of t is compared with x2 of t. So that test integral is modified as j12 of tau is equal to integral minus infinity to plus infinity x1 of t, x2 of t minus tau t tau. Okay, so this is called the cross correlation function. What is this? This is cross correlation function. The function between x1 of t and x2 of t. So j12 of tau depends upon represents the cross correlation. So cross correlation provides the measure of similarity between two different signals. Here x1 of t and x2 of t are two signals. So it provides the measure of similarity between two different signals, that is x1 of t and x2 of t. We are comparing two different signals, that is called cross correlation. Suppose if we compare the signal with itself only, then that is autocorrelation. So note, we have to note that if we shift the function x1 of t by an amount of tau in the negative direction, or shift x2 of t by the same amount in a positive direction, thus this expression will become, see, j12 of tau is equal to integral minus infinity to infinity x1 of t plus tau into x2 of t dt. That is considered as equation number 4. Or we can write as a whole as j12 of tau is equal to integral minus infinity to infinity x1 of t into x2 of t minus tau dt, or integral minus infinity infinity x1 of t plus tau into x2 of t dt. Here x2 of t is shifted by tau units towards right side. Here x1 of t shifted by tau units towards left side. So that's why we can write in any manner, right? So cross correlation function j12 of tau can be represented as either of these either of these two manners. That is equation number 5. So it is minus infinity to infinity x1 of t into x2 of t minus tau dt, or integral minus infinity to infinity x1 of t plus tau into x2 of t dt. Or we can write this as j21 of tau. J21 of tau. This is j12 of tau. 1 x1 of 2 is x2 of 2. So this is x2 j21 of tau is nothing but integral minus infinity into x2 of t into x1 of t minus tau dt, or x integral minus infinity infinity x2 of t plus tau into x1 of t dt, right? So or we can say that j12 of tau is equal to j21 of minus tau, right? J21 of minus tau. Okay. these two are compared like this. J12 of tau is equal to J21 of minus tau. That is equation number 7. That is about the cross correlation. Cross correlation means we are comparing two different signals. X1 of t is compared with the X2 of t, right? So the integral will be modified as J12 of tau is equal to integral minus infinity to infinity x1 of t into x2 of t minus tau dt. Or we can write this as x1 of t plus tau into x2 of t into dt. Right, that is about the cross correlation function. Coming to the autocorrelation function, this is nothing but the comparison of a signal with itself when shifted by an amount tau. Okay, it can be compared with itself only. So autocorrelation of signal x1 of t is denoted by J11 of tau, whereas cross correlation of two different signals is denoted by J12 of tau or J21 of tau, whereas this cross correlation autocorrelation is denoted by J11 of tau. So 11 means one signal is compared with itself only. So it is represented as integral minus infinity to infinity x1 of t into x1 of t minus tau dt, or we can write this as integral minus infinity to infinity x1 of t plus tau into x1 of t dt. That will be considered as equation number 8. And here J11 of tau is equal to J11 of minus tau. Okay, autocorrelation. In autocorrelation function, J11 of tau equal to J11 of minus tau, whereas in cross correlation function, J12 of tau is equal to J21 of minus tau, right? So this J11 of tau equal to J11 of minus tau is nothing but it is an even function. Even function. It is nothing but its mirror image. Mirror image is equal to its original image. That is equation number 9. So it is nothing but even function. So we have to note that autocorrelation function is an even function of tau because J11 of tau is equal to J11 of minus tau. Okay. So now we will compare the correlation and convolution. How these two are related, relation between correlation and convolution. As we already know about the convolution, uh, now we discussed about the correlation. So these two are related as a convolution of two signals x1 of t and x2 of t is defined as rho rho 1 2 is equal to x1 of t convolved with x2 of t. It is defined as integral minus infinity infinity x1 of t into x2 of t minus tau d tau, right? But for rho12 is equal to x1 of t converted with x2 of minus t. So we can write this as a integral minus infinity to infinity x1 of tau into x2 of tau minus t d tau. This is equation number 1 where tau is dummy variable. Suppose dummy variable may be replaced by another variable r. Okay, another variable k, another variable k. Then rho12 of t is equal to integral minus infinity infinity x1 of t into x2 of tau is replaced by k. So here tau is also replaced by k. x1 of k into x2 of k minus t dk. Changing the variables from t to tau, we get rho12 of tau is equal to integral minus infinity infinity x1 of k into x2 of k minus tau dk. Okay, k minus tau dk. This is nothing but J12 of tau. J12 of tau equal to integral minus infinity into x1 of t into x2 of t minus tau dt, right? So this is also in the form of same formula J12 of tau. So rho12 of tau is equal to integral minus infinity infinity x1 of k into x2 of k minus tau dt is nothing but J12 of tau. So where J12 of tau is equal to integral minus infinity to infinity x1 of k into x2 of k minus tau dk. Right? Hence J12 of tau is equal to x1 of t converted with x2 of minus t. Okay, x1 of t converted with x2 of minus t. Where if t equal to tau, then J12 of tau is equal to rho12 of tau. Rho12 of tau, where rho1 is convolution function and J12 is a correlation function. Similarly, j21 of tau is equal to x1 of minus t converted to x2 of t at t equal to tau. It is rho 21 of tau. Okay, rho 21 of tau. And j11 of tau is equal to x1 of t converted with x1 of minus t at t equal to tau. So it is equal to j11 of tau, rho 11 of tau. So j11 of tau equal to rho 11 of tau. We can say that all the techniques used to evaluate the convolution of two functions can be directly applied to find the correlation of two functions. Why? Because these two are equal. Okay, at t equal to tau, these two are equal. J21 of tau equal to rho 21 of tau. J11 of tau equal to rho 11 of tau. Similarly, J11 of tau, J12 of tau equal to rho 12 of tau. These two are equal. And one of the function is an even function of t. The cross correlation and convolution are equivalent. So one of the function is an even function of t. So one function must be an even function. Okay, then cross correlation and convolution are equivalent. If x2 of t is an even function of t, then x2 of t is equal to x2 of minus t, right? So autocorrelation of signal x1 of t is j11 of tau is equal to x1 of t converted with x1 of minus t. If x1 of t is an even signal, x1 of t equal to x1 of minus t is equal to x1 of t, then autocorrelation can be represented as j11 of tau is equal to x1 of t converted with x1 of t only. Okay, that is nothing but equation number 2. So equation number 2 represents an autocorrelation. Okay, equation number 2 represents an autocorrelation and so next coming to the, so that is the relation between correlation and convolution. Okay, relation between correlation and convolution. Next coming to the properties of correlation functions. Properties of correlation functions. What are the properties of correlation function? Okay. Okay. The next coming to the properties of correlation functions. Properties of correlation functions. Yes. See, since the convolution of two functions in the time domain is equal to multiplication of the transforms in frequency domain, as we already know that convolution in time domain will become simple multiplication in frequency domain, right? Simple multiplication in frequency domain. Consider x1 of t is an arbitrary signal, then the transformation of x of t, Fourier transform of x of t is x of omega. Okay, right. If we take the Fourier transform of x of t is x of omega, and Fourier transform of x of minus t is also x of minus omega. So x of omega is nothing but integral minus infinity into x of t into e power minus j omega t dt, or x of minus omega is integral minus infinity infinity x of minus t into e power plus j omega to t, right? If Fourier transform of x1 of t is x1 of omega. Then Fourier transform of x2 of t is x2 of omega. Then Fourier transform of x1 of minus t is x1 of minus omega. And Fourier transform of x2 of minus t is x2 of minus omega. And correlation functions j12 of tau is equal to x1 of t converted with x2 of minus t, or in frequency domain it is x1 of omega into x2 of minus omega. This is equation number 1. And j21 of tau is equal to x2 of t converted with x1 of minus t, or in frequency domain it is x2 of omega multiplied by x1 of minus omega. This is equation number 2. And j11 of tau is equal to x1 of t converted with x1 of minus t, or in frequency domain it is x1 of omega multiplied by x1 of minus omega. That is equation number 3. This is nothing but mod x1 of omega square. Okay, but mod x1 of omega square is equal to 5 times of the energy of the signal x1 of t, right? Because the energy of signal E of x1 is equal to energy of signal x1 of t, that is 1 by 2 pi into integral minus infinity x1 of omega square mod x1 of omega square d omega, as we already derived this one. Okay, d omega. So mod x1 of omega square is equal to pi into E of x1, or this is nothing, x1 of omega square mod x1 of omega square is nothing but x of omega into x of minus omega. That is equation number 4. Using equation number 4, equations 2 and 3 may also be expressed as x1 of omega multiplied by x2 of minus omega is equal to integral minus infinity to infinity j12 of tau into e power minus j omega tau d omega. Okay, equations 2 and 3. So these are the 2 and 3. Okay, x2 of omega into x1 of minus omega, and 3 is x1 of omega into x1 of minus omega. We are writing the Fourier transform for this one. So this is j12 of tau into e power minus j omega d omega. Similarly, x1 of minus omega into x2 of omega is equal to integral minus infinity into j21 of tau into e power minus j omega tau d tau. That is equation number 6. And mod x1 of omega square is equal to x1 of omega into x1 of minus omega, or we can write this as integral minus infinity to infinity j11 of tau into e power minus j omega tau d omega. That is equation number 7. It follows that the Fourier transform of j11 of t is 5 times the energy density spectrum of x1 of t. That is Fourier transform of j11 of t. That is Fourier transform of j11 of t is equal to integral minus infinity to infinity j11 of tau into e power minus j omega tau t tau. That is nothing but mod x1 of omega square. So Fourier transform of j11 of t is equal to 5 times of e of x1, 5 times of E of x1. Fourier transform of autocorrelation function of t, j11 of t is equal to 5 times of E of x1. Okay, that is about the properties of correlation functions. Next, coming to the energy density spectrum. So we already discussed in the earlier unit also. So for electrical systems, signal may be represented as a function of voltage or current. So consider a voltage V of t developed across a resistor R producing a current I of t. The instantaneous power dissipated in this resistor is defined by instantaneous power, that is P of t equal to V of t into I of t. Or we can write I of t as V of t by R. So V of t into V of t by R, that is V square t by R. Or we can write V of t as I of t into R. So I of t into R into I of t, that is I square t into R. Okay. So in both cases, power P of t is proportional to the square of the amplitude of the signal. Amplitude in the sense V of t or I of t, that is square of the V of t or square of the I of t. So if R is 1, then P of t will become V square of t or I square of t. So it is proportional to square of the amplitude of the signal. In general, we can write P of t equal to x square t. X of t may be either voltage or current. So non-periodic signals are called energy signals, as we already know that non-periodic signals are energy signals. So energy is calculated for non-periodic signals. Energy is calculated for non-periodic signals, right? Okay. So total energy of the continuous time signal x of t is defined as E, that is E equal to limit t tends to infinity integral minus t by 2 to plus t by 2 x square of t dt. Okay, x square of t dt. Or we can write this as integral minus infinity to infinity x square of t dt. Similarly, for discrete time signals also it is defined as C equal to sigma n equal to minus infinity infinity x square of n. Okay, the Fourier transform of x of t is x of omega. Then inverse Fourier transform of x of omega, that is x of t, is equal to 1 by 2 point integral minus infinity infinity x of omega into e power plus j omega t d omega, that is equation number 1. So energy E of x of t is given by E equal to integral minus infinity infinity x square t dt. Or we can write this as integral minus infinity to infinity x of t into x of t dt. But x of t expression is equation number 1. Substitute this equation number 1 in one of the x of t place. Okay, so substituting the value of x of t of equation number 1 in equation number 2, we get e equal to integral minus infinity infinity x of t into 1 by 2 pi into integral minus infinity infinity x of omega into e power plus j omega t d omega whole into dt. Now interchanging the order of integration, we get e equal to 1 by 2 pi integral minus infinity infinity x of omega into integral minus infinity infinity x of t into e power j omega t dt whole into d omega. But this integral minus infinity infinity x of t into e power j omega t dt is nothing but x of minus omega. So replace this by x of minus omega d omega. This is nothing but x of omega into x of minus omega is mod x of omega square d omega, right? Okay, but omega equal to 2 pi f. So replace omega by 2 pi f in this expression. So it will become e equal to integral minus infinity infinity x square of dt is equal to 1 by 2 pi integral minus infinity infinity mod x of omega square into d into 2 pi f. This 2 pi gets cancelled. So it will become integral minus infinity infinity mod x of omega square into df, or e equal to integral minus infinity infinity mod x of omega square df. This equation states that the energy of a given signal by the area under the mod x of omega square curve, that is integrated with respect to frequency. And this is also discussed in our earlier unit, that is interpretation of energy density. So energy of a signal x of t is given by E equal to 1 by 2 pi integral minus infinity infinity mod x of omega square d omega, that is equation number 1. So here x of t is the input signal, R of t is the response, and h of t is the system function. So by taking the Fourier transform for these three functions, so Fourier transform of x of t is x of omega, Fourier transform of R of t is R of omega, and Fourier transform of h of t is h of omega. Okay, right? So now h of omega will become uh, the ratio of R of omega, R of response, R of omega equal to product of h of omega into x of omega, or h of omega will become R of omega by x of omega, where let E naught be the energy of the output signal R of t. Okay, so E naught equal to 1 by 2 pi integral minus infinity infinity mod x of omega into h of omega whole square d omega. Since h of omega is 0 everywhere except for a narrow band delta omega where it is unity, which is as shown below. So like this is the h of omega function. Okay, this is a f of t function. It's a spectral density function, means it's a frequency spectrum, and the energy density spectrum is like this. This was already discussed in our earlier unit. So for delta omega tends to 0, E naught becomes 2 into 1 by 2 pi mod x of omega naught square into delta omega, or it will become 2 into 1 by 2 pi into mod x of omega square into delta into omega is replaced by 2 pi f. So it is nothing but 2 pi gets cancelled. So 2 times of mod x of omega naught square into delta f. Therefore, the energy of the output signal is 2 times of mod x of omega naught square into delta f. Sometimes x of omega is called spectrum of x of t. So therefore, x of omega equal to integral minus infinity into x of t into e power minus j omega t dt. The above equation describes the way in which a relative signal amplitude or phase is distributed with frequency. If the amplitude is represented with frequency, then it is called amplitude spectrum. If the same way, equation 1 represents the energy of the signal for different frequencies, and equation number 1 is called as energy density spectrum. Next, in the same way, we can discuss about the power density spectrum in the earlier unit. That is same one. So periodic signals are called periodic power signals. So power is calculated for periodic signals. So x of t is an arbitrary periodic signal. Power of the signal x of t is given by p equal to limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 mod x of t square dt. That is equation number 1. So equation number 1 sometimes referred as mean square value of x of t and is denoted by x square t bar. X square t bar. Therefore, x square t bar is equal to p equal to limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 into mod x of t square dt. So this is power density spectrum. Okay. Next, we will discuss about the Parsells theorem. Parsells theorem for energy signals. Parsells theorem for energy signals. Okay. So the energy E of signal x of t is expressed as E equal to integral minus infinity to infinity x square t dt. That is represented as integral minus infinity to infinity x of t into x of t dt. Let it be considered as equation number 1. We know that the inverse Fourier transform of x of t is x of t equal to inverse Fourier transform of x of omega. That is 1 by 2 pi integral minus infinity to infinity x of omega into e power plus j omega to d omega, right? That is equation number 2. Replacing 1x of t in equation number 1 so that it will become e equal to integral minus infinity infinity x of t into integral 1 by 2 pi integral minus infinity infinity x of omega t e power j omega to d omega into d omega by interchanging the order of integration. So we'll get the e as 1 by 2 pi integral minus infinity infinity x of omega into x of minus omega d omega. We know that for a real signal x of t, the Fourier transform x of omega and x of minus omega are complex conjugates. That is, x of minus omega is equal to x star of omega. So x of omega into x of minus omega is equal to x of omega into x star of omega, or we can write this as x of omega whole square. So e equal to 1 by 2 by integral minus infinity to infinity x of omega, mod x of omega square d omega, or it is equal to 1 by 2 by integral mod x of omega square d into 2 pi of 2 by 2 pi gets cancelled. So finally it will become e equal to integral minus infinity infinity mod x of omega square df. Okay, that is the Parsells theorem for energy signals. Parsells theorem for energy signals. Okay, next coming to the relation between autocorrelation and energy density spectrum. Autocorrelation, that is J11 of tau, and energy density spectrum. Consider any arbitrary signal x1 of the autocorrelation of signal x1 of t is defined as J11 of tau is equal to x1 of t converted with x1 of minus t. That is equation number 1. Here x1 of t is an even signal. So that is x1 of t is equal to x1 of minus t. We can write convolution of two time domain is equal to multiplication of frequency domain. So x1 of t converted with x1 of minus t is equal to x1 of omega into x1 of minus omega, or we can write this as the Fourier transform of j11 of tau is equal to x1 of omega multiplied by x1 of minus omega. That is equation number 2. So proof that we prove this. So Fourier transform of j11 of tau is equal to integral minus infinity infinity j11 of tau into e power minus j omega tau d tau d tau. So it is equal to integral minus infinity infinity x1 of t converted with x1 of minus t into e power minus j omega tau d tau. But by definition of convolution x1 of t converted with x1 of minus t, so it will become integral minus infinity infinity x1 of t into x1 of t minus tau d tau. Right? So Fourier transform of j11 of tau is equal to integral minus infinity to infinity. Okay, infinity j11 of tau is nothing but integral minus infinity infinity x1 of t into x1 of t minus tau dt into e power minus j omega tau d tau, right? So changing the order of integration. So j1 of tau Fourier transform of j1 of tau is equal to integral minus infinity infinity x1 of t into integral minus infinity infinity x1 of t minus tau into e power minus j omega tau d omega whole into dt. Let it be considered as term A. So the delayed version of x of t by tau units. So delayed property. This is time shifting property. So time shifting property. So a Fourier transform of x1 of t minus tau is e power j omega t into x1 of omega. So x1 of t minus tau can be replaced by e power j omega t into e power j omega t into x1 of omega, so that it will become Fourier transform j11 of tau is equal to integral minus infinity infinity x1 of t into e power j omega t into dt into x1 of omega. So let it be x1 of omega can be extracted outside. So x1 of omega into integral minus infinity infinity x1 of t into e power minus j into minus omega t dt. So this is nothing but j11 of Fourier transform of j11 of tau equal to x1 of omega into x1 of minus omega. Hence, if tau equal to 0, then auto correlation j11 of tau is equal to actually j11 of tau is integral minus infinity infinity x1 of t into x1 of t minus 2 into e power minus j omega tau dt, right? So substitute tau equal to 0, then it will become j11 of 0 is equal to integral minus infinity into x1 of t into x1 of t minus 0, that is x1 of t into e power j omega into 0, that is 1 into dt. So it is x1 of t into x1 of t dt, that is x1 square t dt, equation number 1. So integral minus infinity to infinity x1 square d t dt is the energy of the signal x1 of t. Different equation number 1, the value of autocorrelation function at the origin is equal to the energy of the signal, and this is nothing but the energy of the signal. Okay, if the signal correlates perfectly with itself, as the signal is shifted with respect to itself, the amount of correlation will be reduced. The amount of correlation will be reduced. And the autocorrelation function will be maximum at tau equal to 0. Tau of 0 means no shift. Okay. Next, coming to the properties of correlation are as follows. Here we have to note the notations. J11 is autocorrelation, J12 is cross correlation or simply correlation. So here these are the properties, autocorrelation and the cross correlation properties. First one is J11 of 0 equal to integral minus infinity infinity x1 square d x1 square t dt, that is energy function. And second one is j11 of 0 is greater than mod j11 of tau, comma j is not equal to 0. In the first property j equal to 0. So third one is j11 of tau equal to j11 of minus tau, right? And fourth one is j11 of tau. The Fourier transform of j11 of tau is mod of x1 of omega square, that is equal to 5 times of the energy of the signal x1 of t, right? And fifth property j12 of tau, Fourier transform j12 of tau is x1 of omega into x2 of minus omega. And last property is j12 of tau is equal to j21 of minus tau. Okay, that is j21 of minus tau. Okay, this first property was already proved earlier. Here to prove this first property, this is here first property j11 of 0 equal to integral minus infinity infinity x1 square t dt. That was already proved. And second one is comparison of the signal with itself. Comparison of the signal with itself. So is known as autocorrelation, right? Comparison of signal with itself is known as autocorrelation. If two signals are identical, then their correlation is equal to 1. As the signal is shifted with respect to itself, the amount of correlation will be reduced. Okay, therefore J11 of 0 must be greater than mod J11 of tau. Okay, and next one is J1, third property is J11 of tau is equal to J11 of minus tau. J11 of tau equal to J11 of minus tau. Okay, right. So J11 of tau, how it is related, that is x1 of t converted with x1 of minus t. Okay, so by convolution definition, we can write this as integral minus infinity x1 of t into x1 of t minus tau into dt, or we can write this as integral minus infinity x1 of t plus tau into x1 of t dt, that is equation number 1. Similarly, J11 of minus tau is integral minus infinity x1 of t into x1 of t plus tau dt, or we can write this as integral minus infinity x1 of t minus tau into x1 of t, that is equation number 2. So by comparing these two equations, both are identical. Both signals are identical. So hence J11 of tau is equal to J11 of minus tau. Okay, that is third property. Fourth one is J11 of tau is equal to 5 times of energy of the signal x1 of t. So J11 of tau is equal to x1 of t converted with x1 of minus t of t. So Fourier transform of x1 of t is x1 of omega. So taking Fourier transform both sides of equation number 1, we get Fourier transform of J11 of tau is equal to Fourier transform of x1 of t into Fourier transform of x1 of t. That is nothing but x1 of omega into x1 of omega. Okay, so therefore Fourier transform of J11 of tau is equal to mod x of omega whole square, where x of omega whole square is the energy of the signal x of t. So, and one is Fourier transform to J12 of tau will become x1 of omega into x2 of minus omega. So we write J12 of tau is equal to x1 of t converted to x2 of minus t. Okay, the Fourier transform of x1 of t is x1 of omega, and Fourier transform of x2 of minus t is x2 of minus omega, right? Using the convolutional property of Fourier transform, convolution in time domain equals the simple multiplication in frequency domain. So J12 of tau is equal to x1 of omega into x2 of omega. These are the properties of auto correlation and cross correlation functions. In the next class, we will do some problems on this one. Okay, with this I am concluding the today's class. Okay, thank you.